In this section, we're going to be learning about another application of your derivative. And this is just an introductory lesson, and it will be expanded on in section 3.3 and section 3.4. The topic of today's lesson is Extrema. We're talking about extreme y values. And so the formal definition is stated below, the same as it is in your textbook. But it basically is telling you about the highest y value, which would be your maximum. If you know it's your highest y value, it's your absolute maximum, and your lowest y value. If you know that it's your lowest y value, then it's your absolute minimum. If we are unsure, or if there are many maxes and mins, and we have not proven that it's the highest high or the lowest low, then we give them the category of relative extrema, relative maximums and relative minimums. Here's a graphical example of a graph that has multiple maxes and mins, therefore they're all relative maximums and relative minimums. And if your function is closed over an interval, meaning you know the exact endpoints that I have drawn here on the beginning and the end of the graph, then your endpoints are also possibilities for your absolute maxes and mins. And if I take away those endpoints and I put arrows on my endpoints, then those are no longer possible maxes and mins, because that would mean that the function is going on forever. Now, if I take my tangent line and I slide it along my graph, you'll notice that at all of the relative extremum, that the tangent line goes flat. And although I'm not as good at drawing it as I would be if I were a computer system, you can tell that these are all horizontal tangent lines at a maximum or a minimum, and therefore at these points the thing that we know is that the slope of the tangent is equal to 0. And we're going to use this knowledge to help us find algebraically where our max and min values are. Before we do our first example, we're going to be talking about critical numbers in our process. And so I just want to remind you what critical numbers are. They are any value of x that make your derivative either equal to 0 or undefined. And so when I say find your critical numbers, those are the tools that we're going to use to find them. So we're given an equation and we're asked to find any critical numbers of the function. They're just starting us off on baby steps, and so this is just one step of a much larger process. So the first thing we would want to do is derive, and so you can see your product rule. So deriving the first term and leaving the second, plus leaving the first term and deriving the second. And then I simplify it. And this was the reason that you were always factoring out whatever you could and simplifying your derivatives, because we're about to set it equal to 0. So we get 2x times 2x squared minus 4. I can factor out another 2, and I get 4x times x squared minus 2. Now, a critical number is anything that will make this equal 0 or go undefined. Because it's a polynomial, we know it's not going to go undefined. So I only need to worry about when 4x equals 0 or x squared minus 2 equals 0. And so my critical numbers are x equals 0 and x equals plus or minus square root 2. You'll notice in this example that the first two steps are identical to the previous slide. So start by finding your derivative, and you get 3x squared minus 12. Again, it's a polynomial, so it doesn't go undefined, so we don't have to worry about that. And we just set it equal to 0. We solve for x. And we get x equals plus or minus 2. And so my critical numbers are plus or minus 2. If I had an unlimited domain and I was studying this function from the beginning of its domain to the end of its domain, an unlimited domain would be from negative infinity to infinity. And so my intervals would look like this. Negative infinity to negative 2, negative 2 to 2, and 2 to infinity. Remember, these are all x values because they are your domain. And then I would test these intervals. But they put me on a restricted domain that's closed. And so I'm picking up at 0 because that's my lowest x value. And my first critical number that fits is 2. Negative 2 isn't in this particular problem. And so then I go from 2 to infinity. So 0 to 2 and then 2 to infinity. Now on step 4, it tells us to test our intervals. And we're not interested in the value of the function because it would be different for every value within the interval. But what we're interested in is the sign. What's the slope over those intervals? Because we want to know, is this function increasing in y values or decreasing in y values? So the first thing I would do is pick a number between 0 and 2. So I'm going to test 1. I'm going to choose to look at 1, and I'm picking this randomly. And so I find f prime of 1 because I want to know what the slope is doing. And f prime of 1, when I plug it in, becomes 3 times 1 minus 12. And again, I'm not interested in the value. I'm interested in the fact that it has a negative value. And then in the second interval, I'm going to choose 3 because that's between 2 and infinity. And so f prime of 3 becomes 3 times 3 squared minus 12, and 27 minus 12 is a positive value. And so I put a plus under that interval. Now, visually, what this shows me is that my function is decreasing. So I draw it, and I say my function was decreasing until it hit 2, and then it's increasing. Now remember, the slope describes the original function. And so what we've just drawn is the shape of f between 0 and, sorry, this shouldn't be infinity, that should be 4. And so between 0 and 4, it's decreasing and then increasing. And so I know that I have a relative min at 2 because that actually draws a minimum for you. And so now I want to know whether it's an absolute. So when I choose my absolute, I need to find the value of the original function at both of my endpoints and at any critical number in between. So because I want to know a relative maximum and a relative minimum, I need to know the absolutes. So f of 0, f of 2, and f of 4, I'm going to test them all and find out what they equal. So plugging in 0, I get 0 cubed minus 12 times 0, which is equal to 0. And plugging in f of 2, I get 8 minus 12 times 2, which is 24. 24 minus 8 is 16. And then f of 4, I get 64 minus 12 times 4, which is 48. So 64 minus 48 is positive 16. So going back again, f of 0 was 0, f of 2 was negative 16, f of 4 was positive 16. So looking at the y values, f of 4 gives me my highest y value, and f of 2 is my lowest y value. And so I have an absolute max at x equals 4, which gives me 16, and I have an absolute min at x equals 2, which gives me negative 16. And that's my final answer. Okay, so one more example of the same type of problem, and then I'm going to let you do a problem. And so start off by finding your derivative. This is the quotient rule. So we derive the top and keep the bottom, subtract keeping the top and deriving the bottom, and then it's over the bottom squared. So simplifying, I get on top, I get x minus 2 minus x, which the x's will cancel, and it's over x minus 2 quantity squared. So I get negative 2 over x minus 2 squared. And so as you can tell, I don't have any zeros because this is never going to equal 0 because the numerator is a negative 2. And then it goes undefined when x equals 2, because x minus 2 equals 0 when x equals 2. So my critical number is just one item this time. It's x equals 2. So looking at my interval, I'm going from 3 to 5. 2 is not within my interval, and so I don't have anything that's changing. I know that from 3 to 5 it's going to be behaving the same way, and so my whole interval is just 3 to 5. If I plug in a value and test it, so let's make x positive 4, and so 4 minus 2 in my denominator is 2, square it is 4, that makes that negative 1/2. And so this is decreasing over the entire interval. And then, therefore, by default, we know that when I prove it, that I'm going to have an absolute max at 3 and an absolute min at 5. And so plugging in my values, I have f of 3, and I get 3 over 3 minus 2, which is 3. And then f of 5 is 5 over 5 minus 2. And so I get 5/3. And 3 is obviously bigger than 5/3, so my absolute max is at f of 3, and my absolute min is at f of 5.